Hello students, it's Dr. Sansom here. I promised you a video about pH calculations, so here we go. The first thing that we need to know is that the pH calculations are based on the equilibrium for the autoionization of water. Okay, so that means when you have water, pure water all by itself, it is going to, some of it is going to dissociate and turn into hydrogen or hydronium ions and hydroxide ions. So this is that actual chemical reaction. Water reacts with itself. It's an equilibrium reaction. We make H3O plus and OH minus. Sometimes you also see this written as just one water molecule making H plus and OH minus. And either way is acceptable. As we talked about in class, H3O plus and H plus are pretty much used interchangeably. H3O plus is closer to reality just because protons don't generally float around all by themselves. So this is an equilibrium reaction and it has an equilibrium constant, Kw. We have the W there, that's for water. It's just an equilibrium constant like any other. And so we've got our products over reactants. Because our reactants are both liquid, we don't include them in our equilibrium expression. And we get H3O plus times OH minus, or H plus times OH minus, again, using H3O plus and H plus interchangeably. And this is, in fact, our very first equation that we're going to need to be able to deal with this stuff. And the value of Kw at 25 degrees Celsius is 1 times 10 to the minus 14. Okay, so I'm going to just start a little collection here of equations that are going to be useful for us. The first one that we've got is 1 times 10 to the minus 14, that's our Kw, equals our concentration of H3O plus times our concentration of OH minus. This is just our equilibrium expression for the autoionization of water. Now, this is a super useful thing. If I know the concentration of H3O plus, I can find the concentration of OH minus. I just divide by the concentration of H3O plus on both sides, so I can rearrange this pretty easily and figure out what that is. But sometimes we also want to be working with easier numbers that don't have those exponents in there. So this is where we get our kind of second set of equations, which is our pH. So P is our operator, and it means negative log base 10 of. Okay, so if I want pH, I'm going to take the negative log base 10 of our H3O plus concentration. If I want my pOH, I'm going to take the negative log base 10 of my OH minus concentration. Okay, so P is just an operator. It tells you what to do, take the negative log of. And a log base 10, is just the exponent essentially of that number in a base 10, like we have up here where we have 1 times 10 to minus 14. The log of that would be minus 14. The negative log is 14. So this just translates those numbers into something a little bit easier to work with. So now what I want to do is just rearrange this top equation here. And we're going to take the negative log of both sides. Okay, so I'm going to do the negative log of 1 times 10 to the minus 14. That is 14. Like I just said, negative 14 is the log. The negative log will be 14. And if I take the negative log of H3O plus, that's just the same thing as my pH. And when I have these two multiplied together in my log rules, that means I'm going to add together the result, and that negative log of OH minus will just be POH. So these two equations are identical, just rearranged to use either with pH and POH or to use with our H3O plus and OH minus concentration. Then we've got these other equations down here for pH. Sometimes we don't write the log base 10. It's just kind of assumed that we know it's the log base 10, and so we don't worry about that. And these are also, sometimes you know the H3O plus concentration and want to find the pH, and this equation is useful for that, but sometimes you know the pH and you want to find the H3O plus concentration. So if I actually, I I'm going to do 10 to the negative both sides here. So I'm going to do 10 to the minus pH. That's going to get rid, the 10 to the minus gets rid of my minus and my log. That equals my H3O plus concentration. So if I know the pH and I want to know the H3O plus concentration, that equation is a better one to use. And likewise, we've got the same thing over here for our OH minus concentration, just using the POH instead. So these here are our 6 equations in total that we're going to use for all of our transformations. The 2 at the top that are based strictly on the autoionization of water, and then these 4 equations that are for the pH and POH to transfer between pH units versus our regular concentration units. Okay, so now what I'd like to do is a couple of example problems that show you how to use these equations just to solve problems, okay? So the first one that I have here is, what's the concentration of hydrogen ions in a solution with a pH of 3? This one's pretty straightforward, very easy to do. It's just 10 to the negative pH. So we'll have 1 times 10 to the minus 3 equals our concentration of H plus. 10 to the minus 3 because our pH is 3. Very straightforward. Now, what happens if you have a pH and it's not a whole number? So if it's 3 or 2, that makes it easy. It's just the exponent, but you're not really supposed to have 10 to the minus 2.7 or something like that. So if that's the case, what you want to do is just put it into your calculator and calculate 10 to the minus 2.7, for example, and it'll give you a coefficient. So I'll do that really quick. So 10 to the minus 2.7, and I get 1.99 times 10 to the minus 3. Okay, so my calculator is just going to convert it basically from this like not okay notation over here to something that we recognize in our regular scientific notation over here. So if you have a not whole number, sometimes you have to use your calculator, but also you can use your brain to think about what should that number look like. So if it's 10 to the minus 3, that's like 0.001. And 10 to the minus 2.7, that's going to be a little bit larger than 10 to the minus 3. So I actually got something like 2 times 10 to the minus 3, which makes sense for what I expect it to be. Something larger than 10 to the minus 3, getting closer to 10 to the minus 2. Okay, now that's our first question. Pretty straightforward, pretty easy. Let's do another one. Now we're going to try to convert between these different units and different representations. So I know in my next problem, I'll just make a new screen. I know that my concentration of hydrogen ions is 2.3 times 10 to the minus 9th. And I want to know, what is my POH of the solution? Okay, so now I'm going to think about how can I get this? So the first thing I'm going to think is, if I know my H plus concentration, I can find my pH. I just take the negative log of my H plus concentration. So 2.3 times 10 to the minus 9, and I'm going to take the negative log, and I get my pH equals 8.64. Because I had the 2 numbers in the coefficient, 2 sig figs in the coefficient, I'll have 2 decimal places here. So 8.64 is our pH. Now, how do we find the POH? We're going to use our equation, pH plus POH equals 14. This is true at 25 degrees. The vast majority of the problems that you're going to see, pretty much all of them, are going to be at 25 degrees, so you don't have to worry about that necessarily being different. So my POH here is going to be 14 minus 8.64, which gives me 5.36. So pretty straightforward to use these 6 equations that we've got. One that tells us how hydrogen ions relate to pH, or actually I guess there's 2 of those, right? Both forms of that equation. Our 2 equations that relate our OH minus concentration to POH, and then our equation based on the KW that relates our H plus and OH minus concentrations, or our pH and POH. So using those, we can basically get to whatever combination of things that we need. Now, we have another couple of problems that are a little bit more challenging. The first one is a dilution problem. So how much water should we add to 5 milliliters of 12 molar hydrochloric acid to make a solution with pH equals 2. Okay, so now this one's a little tricky because we have to recognize something that is implied in what's written here. They told us the pH, and the pH is just a code word. It's like a different way of writing out our hydrogen ion concentration. So I actually know what the concentration of my diluted solution is going to be. It's 10 to the minus 2 or 0.01. Because they told me I wanted a pH of 2, so 0.01 would be my concentration of H+. So now I can use my M1V1 equals M2V2, the dilution equation. I've got 12 molar times 0.005 liters, or 5 milliliters. And I want it to be 0.01 molar times X liters. We don't know how many. When I solve for this, I'll get X equals 6 liters. And my question asks how much water should I add? So that would be 5.995 liters. And just for the record, when you are making a solution with acid and water, you always add the acid to the water and not the other way around. So really, we shouldn't say how much water should we add, but that gets us to the calculation that we need. Okay, now there's one more problem that I want to do, and this is about involving some stoichiometry. So now taking this concept of pH and kind of connecting it with some of the other concepts, like we did in this one, we're connecting it with dilution. And in this last problem, we've got 74.1 grams of calcium hydroxide. And we're going to dissolve them in a total of 20 liters. So we get 20 liters of solution. And we want to know what is our pH. Okay, so for this one, we know in order to get pH, we're going to need concentration of hydrogen ions, but we've got calcium hydroxide, so we're going to have to start with our concentration of hydroxide ions. So the first thing we've got to do is figure out how many moles we have of calcium hydroxide. So we do need to know the formula CaOH2 for our calcium hydroxide. And it turns out 74.1 is actually the molar mass of calcium hydroxide. So this is just 1 mole of calcium hydroxide. And this is a thing to pay attention to. Some of our strong bases, like NaOH, LiOH, KOH, just have 1 hydroxide per mole, but some of them, like calcium hydroxide, have 2. So we're going to have to take our 1 mole of calcium hydroxide and turn it into 2 moles of OH minus. That's just what happens when you put it in water. Because it's a strong electrolyte, it dissociates completely, and we end up with these 2 moles of hydroxide ions in solution. So when I multiply this out, I end up with 2 moles of hydroxide ions in my solution. And so if I want to find my concentration of hydroxide, it's going to be 2 moles in 20 liters, which is going to give me 0.1 molar hydroxide. Okay, now 0.1 molar hydroxide, I should say we've got here, forgive me for just a minute, I'm going to pay attention to my sig figs. Our 20 that they gave us had 2 sig figs, and our 2 here really has 3 sig figs because we started with the 74.1. So this is 0.10 molar hydroxide ions. Okay, now the question asks us what's the pH. So I'm going to take the negative log of my OH minus concentration to get the POH. And that's going to give me 1. Two decimal places because I've got 2 sig figs in my number that I'm putting in there. Okay, that's my POH. To get my pH, I do 14 minus the POH, which gives me 13.00. So that's my pH of this solution. I'm going to stop and check myself. This is a calcium hydroxide solution. I know that's a strong base. It's reasonably concentrated. So I do expect it to have a high pH, above 7 and closer to 14. And that's what I get here. So that's an example of how we do several different types of calculations with pH and pOH, how we can use that together with stoichiometry, together with dilution and other things that we know about in order to figure out something that we need to know about that solution. Knowing the pH is helpful because it gives us a sense of whether something is acidic or basic, and therefore what the properties are going to be, how dangerous it might be, what hazards are associated with it, and also how's it going to react with other substances when we use it in a chemical reaction. I hope that's helpful for calculating pH, doing several examples for you, and I hope you have a great day.